Okay, so we're going back and essentially moving into smaller scales slowly. This is a third session, the diffuse interstellar medium, and we will start this session with a review talk by Naomi McClure-Griffiths talking about key results from H1 surveys over the decades.
Okay, well, thank you very much. It's a pleasure to be here. It's wonderful to see so many ISM people in one room. It's just that I'm cheering about this. This is exciting. I have the diabolical slot of the post-lunch in a first-day jet-lagged sort of conference. So I'm going to do my best to try to keep you awake. If you snore, I will point you out. So I'm going to talk about key results, key being as defined by me, over the decades, which really is largely limited to the decades of which I have experience. So atomic hydrogen, there we go, okay. Atomic hydrogen is a wonderful thing. It allows us to trace out the cycle of galaxies. So by using atomic hydrogen, we can trace out how galaxies work in their almost entirety. We can trace gas inflow, we can trace gas outflow, the conversion from diffuse atomic through to molecular gas. We don't do so much on this part of the star formation bit, but once those stars are formed, they start forming bubbles. Those bubbles continue and get bigger and bigger. You add in supernovae, you get supershells and very large things that go back into the diffuse interstellar medium. And we can trace a large fraction of this by looking at the atomic hydrogen properties and distribution around the Milky Way. And because this meeting is going to move into magnetic fields, I'm not going to leave them out entirely, because I think we often do forget to talk about magnetic fields when we talk about atomic hydrogen, and it is important to remember that they are there and that they have a significant influence. So I am going to come around to magnetic fields as well. We need something that makes a really nice picture for magnetic fields. Using a bar magnet is really not so good. Jay Lockman showed a bit of Carl's thesis this morning. He showed a picture, or he showed the front of it and how it scanned out. He scanned a whole bunch of pages and sent them to me, and I think they are amazing, Carl. These pages are incredible. I had never seen anything like this, which shows my age, I guess, as being significantly younger. So I think we've come a long way from using A's and B's as contour levels to now being able to visualize our data and things like this, which is from the Galactic Sky Survey conducted with Parkes. Just an example of the way that we are looking at data now in much more complexity. Although I don't know that the answers we're coming up with are actually that much more significant than the ones that Carl came up with from his data. So the first bit is just to take you through a couple of surveys, just to remind you. At the bottom of slides where somebody's going to be talking about something like this, I've got a link to their talk, as in I've put their name. If I forgot yours, I apologize. So our H1 emission surveys have come a long way. We now have surveys like GALPHA H1 at a few arc minutes angular resolution and spectacular velocity resolution, producing incredible images like this. We had the state-of-the-art for a while, was the lab survey at 30 arc minute angular resolution, and that tells us quite a lot as well. We now have both the southern and the northern components of two surveys which are being put together to be called Hi for Pi. So this is the gas survey and the EBIS surveys, which are in the sort of tens of arc minutes, 10 to 16 arc minute resolution. Those have all been single dish type surveys. The galactic plane has been pounded away with the interferometric plus single dish combination of the Canadian Galactic Plane Survey, as shown down here. That covers the third quadrant, galactic quadrant, and around a bit. The VLA Galactic Plane Survey covering the first galactic quadrant, and well, this one covers the second and third. This one covers the fourth here. And there's a little tiny gap which is largely filled in by GALPHA H1. So the H1 emission and absorption surveys, I call them because these ones, although they are largely intended to look at the H1 emission, you can see these nice little white dots here. Those are continuum features which are observed in absorption, and those have been used extensively to measure the properties of the H1 in the galactic plane through H1 absorption spectra. There have also been a number of surveys that are specifically targeted towards H1 absorption, and those ones, I like to think of the absorption surveys as giving us the properties like temperature, density, pressure, and the emission surveys is giving us the morphological context in which those things sit. So some of the targeted H1 absorption surveys, nicely summarized in this figure from Claire Murray, comparing the RMS noise versus the number of continuum sources per square degree. The mapping surveys up here and the more recent surveys down here, probing various different things, including the Heiles and Troland survey there. So all of those have been used enormously to try to understand this cycle again. And the part that I want to focus on here first is talking about this upper bit where we're looking at H1 shells and supershells. And the reason I start here is because this is where I started when I started my PhD, a not so indescribably long time ago. I was handed a paper by this guy called Carl Heiles from 1979 and another one from 1984, and said there's these things called holes, can you find some? And I did. So Carl showed us extensively with a large catalog of H1 supershells that these can be large-scale energetic objects traced in their atomic hydrogen emission as holes surrounded by dense walls of atomic hydrogen. They're energetic with energies, expansion energies of 10 to the 51 to 10 to the 53 ergs, and can range from sort of tens of parsecs up to kiloparsecs in scale, formed by tens to thousands of massive stars. And this is an example of one here. This is from the Southern Galactic Plane Survey, and where it's dark, you can see there's very little H1, and where it's bright, there's a lot along the edges. Now, we also know that these can form chimneys or fountain-type structures where they grow so large that they break out of the disk of the galaxy and they blow their contents out into the halo, and that they are all over the place. When you look around the Milky Way, you see these all over the place. Many of them are expanding still, and many are not. They're the sort of perfect laboratory for doing ISM evolution because they do all kinds of wonderful things. They blow out of disks of galaxies. They also pack the gas together so that it can cool and condense. And so you can see sort of the entirety of ISM evolution just in these particular objects. And the shell walls compress gas with brightness temperature jumps of, like these ones here, a factor of 10 over a few tens of parsecs. And the gas then cools down in these dense walls, and you see cool lines that are something like a few hundred Kelvin as estimated from the line width. And indeed, you can even start to see molecular clouds forming along the edges. So there's some examples of that. So this will be covered a bit in Joe Dawson's talk, or covered extensively in Joe Dawson's talk tomorrow. But you see here, these blue clouds are CO clouds forming along the edges of these shells, these supershells that we observe in H1. The H1, furthermore, has very cold narrow line widths. And the big question is, do the supershells actually form molecular clouds in situ along their edges, or are they actually just collected from little parcels of molecular gas which get collected up into bigger clumps so that we can see them along the edges of the shells? And I'll leave it to Joe to answer that question. But you can form some very, very big molecular clouds in between shells, like this example here from Dawson et al. 2014, where there's a giant molecular cloud formed at the intersection of two H1 shells, where you brought them together and collected this extremely massive cloud. There's more on this theme. fairly recently from Elarova and Palou, where they're looking at the correlation of CO and supershells around the galaxy. We can also learn a lot about the distribution of supershells in the galaxy. So the image up on the top right is actually from my PhD thesis, where I took Carl's catalog and my own poultry catalog over on this side and put them together looking at the galactic distribution of supershells. We drew a lot of conclusions from that. One thing you tend to see is that the larger shells are in the outer galaxy. And that's not too surprising. They can survive longer there. Differential rotation doesn't smash them up quite as quickly as it does in the inner galaxy. And the scale height is probably a little bit larger as well. Some more recent work doing automated shell detection has been finding hundreds and hundreds of shells throughout the Milky Way. They are using the Leiden-Argentine bond survey to try to find these loop-like structures throughout the disk. And these two papers here, this one's been finding a surface density of shells at about the solar circle of about 4 supershells per square kiloparsec, and that is increasing out to 8 or so per square kiloparsec in the outer galaxy. I'll just add a caveat on here, which is probably a bit rude, but if you go outside and you look up in the sky on a cloudy day, you can find all kinds of loops. And they're not necessarily all formed by something like massive stars. So we have to be careful in what we're doing to make certain that these things they're necessarily formed by some process or whether they're just a random thing. But that said, there are lots and lots and lots of supershells in the galaxy, and they do provide excellent fossils for tracing the past history of star formation. So moving along in our cycle, well, these supershells can get very, very big, as I said, and exceed the scale height of the disk and blow out into a nice big chimney. So Carl led the way with a ton of papers on disk-halo interaction. I'll just back up and say something I meant to say earlier on. In preparing for this talk, I just did an ADS search of all first author publications by Carl. And I then went into my group meeting and I said to my postdocs, you guys don't know this guy, but he has done everything in the galaxy, everything. And I was kind of surprised. I didn't actually know. So you should go back and read papers from the 60s. Don't stop when you were born, I think is a good idea. So Carl wrote some papers on intermediate velocity clouds in the late 60s. He's written a number of different things about some theories of clustered supernovae versus the halo, and considering what happens in the disk interacts with the halo entirely. So Carl showed us another nice contour map. This one I can understand a bit more, of some intermediate velocity clouds as potentially condensations from a thermally unstable halo. These had large velocities because of the acceleration towards the plane was the idea, and these are sort of the initial halo cloudlets idea. There was something buried away in one of these papers about this newfound thing called the Parker instability. I didn't realize the Parker instability was a newfound thing, but it was at that point. So what do we see now, having moved forward a number of years? Well, we know for certain that you transfer H1 to the halo, to the lower halo, from processes in the disk. So the example of the Ophiuchus superbubble, which we've heard about already today, shows high latitude plume features with diameters of sort of 100 parsecs or so, sitting up 3 kiloparsecs above the disk, and they're connected all the way back down to the plane via these little whiskers, oops, wrong way, that are along the side here. And the green is H alpha and the purple is the H1 there. So Jay showed us quite a lot about little clouds, the so-called disk halo cloudlets. The lower H1 halo is indeed very cloudy, so these are J's clouds, follows up from Alison Ford's work. These little tiny features here co-rotating with the disk, but isolated up above the plane, with scale heights up to a kiloparsec or so. And the belief is that these are, in a lot of cases, correlated with what has happened in the disk. So by comparing the distribution of clouds in two different regions around the tangent point, so from Alison Ford's work, over here in the first quadrant where you're near to the very exciting end of the bar and the major spiral arm, versus over here in the fourth quadrant where you're over a so-called sort of minor spiral arm, and you see much more structure, much more halo cloudlet structure. I'm going to stop doing that. In this region over here, where there's been a lot of star formation in the disk, versus the fourth quadrant region, where there's been very little, comparatively little star formation in the disk. And the idea is that you fluff up more from the disk where you've had a lot of star formation activity than you do in the regions where you haven't had as much star formation activity. It's sort of an obvious kind of conclusion, but it's a nice way of connecting what you see in the lower halo to what you see in the disk. Now we know that there are clouds, 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 and more clouds. As Jay talked about, these are some more examples from the Galpha H1 survey, which are showing us, more interestingly, that there's velocity gradients across these very small-scale clouds, that they have sometimes very narrow line widths, indicating that they're quite cool, and that it's an extensive population of clouds. Now that goes against sort of what we've been thinking for a long time about the rest of the interstellar medium and its blobby sheet-like structure, for which there's extremely good evidence that exists. So the next part is on probing H1 from the warm neutral medium to the cold neutral medium. And this covers many, many, many papers of Carl's leading from all the way back in his PhD times up through the very important recent work on the Heiles and Trollin survey, probing the properties of the cold neutral medium through to the warm neutral medium. So the Millennium survey found that about 60% of H1 is in the warm neutral medium, that there's no variation as you come down to the galactic plane versus going up above. So we don't see a significantly different population of gas as you come down into the disk. With median spin temperatures for the cold neutral medium of about 50 K or so. And the pressures, I think this final point is something that I find very interesting and important, is that the pressures indicate that the cold neutral medium must be in blobby sheets. I think this is where we fail as interstellar medium astronomers. Blobby sheets does not inspire a lot of confidence amongst our astrophysical colleagues. I think we should work on something that sounds a little bit more interesting, but blobby sheets it is, with length to thickness ratios that can be up to almost 300. So very, very extreme properties. But that's something very interesting about the interstellar medium that I think we're learning more about as I'll talk about in a little bit. We know that the cold neutral medium is distributed throughout the disk. So if you look in the disk, we see it all the way out to galactocentric radii of 25 kiloparsecs. What we're looking at here is from Simon Strasser et al.'s paper, where the top panel here is H1 in emission, and the bottom is H1 in absorption. So these are absorption components detected towards many, many sources through the galactic plane. And the correspondence is, not surprisingly, very good. But what I think is amazing is that you're seeing out in these very outer regions here, so out to 20 kiloparsecs or so, you're starting to see H1 absorption all the way through the disk at very far distances. The cool phase temperature from Strasser's work, and then following on work from John Dickey et al., is very similar to what you see from the Heiles and Trollin survey, around 50 Kelvin everywhere is the key there, so that they see the same temperature of gas from 0 kiloparsecs, well, a few kiloparsecs galactocentric radius out to high galactocentric radii. From this, we can infer a bit about the cold neutral medium fraction in the disk. And what we see here is that the cold neutral medium fraction in the disk, so here we're looking at the log of the spin temperature, which you can relate via your handy dandy equations to looking at the cold fraction, is pretty much flat from 8 kiloparsecs out to 25 kiloparsecs. So if the temperature of the cool clouds is the constant as we move through the disk, then the cold neutral medium fraction is constant. So it appears the cold neutral medium fraction doesn't vary with galactic position. And that's a bit puzzling, I think. I think that's something that we need to think a lot more about. And this is where comparisons with looking at other galaxies tells us something interesting, because there the environments change as well.
Sorry, is this per volume or per mass, this function?
That was by volume, I think. Cold neutral medium in special environments, so we'll hear a lot more about this, I expect, tomorrow from Minyoung Lee. But here we're looking at work from Snezana, Stanimirovic, and Lee et al. As well, around the Perseus molecular cloud. So now here we're looking at what should be a special environment in the sense that you're not looking in just the standard ISM everywhere you go, but you're going into places near around giant molecular clouds where you might expect things to be different. But the cold neutral medium in and around the giant molecular clouds, as traced by H1 absorption towards all these background sources, is typical of what you see in other parts of the galaxy. You do see a slightly higher fraction than in the random field, so they say 0.33 versus 0.22 in the cold neutral medium fraction, but otherwise, comparing the properties, the spin temperature, the green here is the Perseus data, and the gray is the Heiles and Troland, and they're very similar in both cases. Continuing on my whirlwind tour, how much unstable gas is there? So we saw at the very first slide, I think, that Adam showed this morning, of a pressure diagram, something that looks similar to this. This is from Hill et al. Simulations, where you see gas in the stable 2 phases, and then there's the unstable phase, which is populated to some percentage. And one of the things that we want to know in the Milky Way is how much gas is in that unstable phase. And from the Millennium Survey, Heiles and Troland gave us something like 48% of the warm neutral medium is in the unstable temperature regime of 500 to 5,000 Kelvin. But that was a fairly uncertain sort of number. So Claire Murray and Snezana, Stanimirovic and collaborators have been looking at this much more extensively with the 21 sponge survey. And other people before also have been doing this a bit, trying to figure out the unstable neutral medium fraction. And that comes down from the 48% that we see with the Heiles and Troland, through 30% of Began et al., 28%, and moving on down to only 20% in the recent work by Claire Murray et al. I assume she'll tell us more about that tomorrow. That's coming more in line with what you see from the simulations of the galaxy, so it's coming around to where we sort of expect things maybe would be. But there's a lot of implications in it, and also implications in the fact that they see a maximum spin temperature coming in around 1500 Kelvin, even though they could see higher, directly detect higher. Now, what's my timing? Okay. So, continuing on my cycle, the next part is to bring in the magnetic fields. So the last thing that I want to do is to not forget that magnetic fields and H1 have an important relationship. And I was just talking to somebody just, 2 days ago who was saying, how can H1 and magnetic fields have an important relationship? Atomic hydrogen is atomic, right? So And we have to remember that wherever you see atomic gas, there's some significant ionization fraction, and then you can bind the magnetic fields to the atomic gas via the ionized gas that's present as well. So Carl's given us a wonderful set of work on that, dating back from work on supershells in 1989 and various different reviews. Here I'm focusing just on the H1 part, not all of his other molecular work. So this is the NCP shell. Carl worked on looking at the magnetic fields associated using H1 Zeeman measurements along those positions here. It's a little bit hard to see. But what he was measuring was morphologically distinct shells and then a comparison region, and finding that the magnetic fields were on the sort of magical 6 microgauss kind of level along the line of sight. That the parallel component of the magnetic field was larger in shells than in non-shell regions in general, and that therefore the magnetic pressure had to dominate the thermal pressure by a very large factor. The continuation of similar sorts of work, but going much more deeply and more extensively in the Heiles and Trollin 2005, found median magnetic field, total magnetic field here, of about 6 microgauss. This is the truly magical number. Many small or zero values if the field is randomly oriented. But when you go to areas where it's morphologically distinct, like these type of things here, then where the field must generally align with the shell, it favors stronger detections. And that's why you see this kind of difference that was found in the shell versus non-shell region. Now we know now from various other ways of looking at things that there are lots of magnetized supershells, plenty of magnetized bubbles. You can do it in the H1 Zeeman case. You can compare the H1 to Faraday rotation measurements. And this is an example of that here. What we're looking at here is diffuse polarized emission at a particular Faraday depth. And there are these yellow slices here are particular arcing filaments. And as we move through different Faraday depths, which probes different magnetic field orientations and strengths, you see that structure changing. So you move across the structure as we come down here. And this agrees very well with an H1 shell, which is what we're showing here in the bottom plot. And by putting together the Faraday rotation measurements from the diffuse polarization with the H1, they estimate a magnetic field strength of about 20 microgauss in this supershell. And there have been a couple of other supershells with very large magnetic field strengths indicated. So there's definitely something to be said for strong magnetic fields in organized objects. We also know from the measurements of the regional Crutcher cloud, which is what I'm showing here. So we're stepping through slices, velocity slices. This is the regional Crutcher cloud in H1 self-absorption, that it has magnetic fields associated with it. Now, this particular cloud is wonderfully filamentary. It has widths that are less than 1/10 of a parsec in these little hair-like filaments that you can see here, and some of them extend up to 17 parsecs in length with very high aspect ratios. And importantly, they're aligned with the magnetic field as probed by starlight polarization measurements compiled by, guess who? Somebody sitting in the front row. So we can see that the filaments are aligned with the magnetic fields here. Now this type of idea has been carried out much more extensively recently, and we'll be hearing more about this in Susan Clark's talk, where they're looking at fibers in the H1 distribution and those being aligned with magnetic fields as traced by Planck data. So that's what we're looking at up here. This is Galpha H1, and you see this wonderful fibrous structure, and then the magnetic fields aligned along with it. And more work from Peter Kalberla et al., again on cold filamentary H1, very narrow widths, long aspect ratio fibers. So the ISM seems to be filled with this wonderfully sort of fibrous structure that seems to be aligned with magnetic fields. And because we can't forget that there is gas coming in, we heard about the Smith cloud earlier. So this is the Smith cloud over here, overlaid with rotation measures towards extragalactic background sources. So these are from the NVSS catalog of rotation measures. And what Alex Hill and collaborators found is that a portion of this Smith cloud down here is lined up with some measurements of the rotation measures that indicate that there is a significant magnetic field associated with the Smith cloud. And I think Bob Benjamin was the first to find this, and Alex carried through on it. So we had also found before, this is a cloud associated with the Magellanic leading arm. And again, rotation measures all here. You can see that these are all the foreground structures, but something looks different where you see the high velocity cloud. And you can subtract this foreground, as we did there, in order to get the signal out. And this is what you see, this very strong indication of a Faraday effect associated with a high velocity cloud. Now both of these measurements here, both the Smith cloud, here we're looking at the H alpha, but the same idea, the Smith cloud and this cloud associated with the Magellanic leading arm, both give indications of ordered magnetic fields on the order of a few microgauss as their lower limits. So it seems that magnetic fields are important not just in shaping the ISM and shaping the supershells, but also in allowing infalling gas to have magnetic fields, which may or may not be important. My little lights turn yellow, so I'm going to summarize. So supershells are the movers and shakers of the interstellar medium. They're the places where you can blow gas out of the disk. They're the places where you can collect molecular gas, and you can cool down gas along the edges. So I think they have an important role in understanding how a galaxy works. We now know, thanks to work from Carl and Tom and many others following on from that, we know a lot about the properties of the cold neutral medium, the unstable neutral medium, and the warm neutral medium. The cold neutral medium exists a long way out in the galaxy, out to 25 kiloparsecs. The unstable neutral medium exists, but it's limited in its temperature. And the warm neutral medium in its warmest state is still hard to find. The cold ISM, in the disk anyway, is sheet-like or filamentary or blobby sheets, or however you want to describe it, but they tend to be thin sheets, fibrous, magnetized structures. And magnetic fields in general should not be separated from our discussion for H1. We should keep these two linked together because they do have an important interrelationship in the cold neutral medium, the warm neutral medium, and the high velocity sky. And almost all of that is thanks to work that Carl sort of pioneered through. So thank you.
Let's see.
Thanks. Naomi, it's about the unstable neutral medium. The conclusion about instability is based just on thermal pressure, right? But thermal pressure is just one part of the total pressure. There's also magnetic pressure, cosmic ray pressure,
Yep.
turbulent pressure. So why turbulent pressure alone? Why thermal pressure alone? Is it enough to conclude instability? Just singling out one component of pressure just because it's easier to measure?
Well, I guess that kind of leads into we shouldn't always separate magnetic fields from our discussion of H1. We do need to think about the other forms of pressure, and you're right. So thermal pressure matters as well. I'm going to leave that because we're going to have an enormous talk from Claire tomorrow, who probably will pick up on these points, or today, in fact. So we'll leave it to Claire to answer that, and if she doesn't, then you can ask it again.
Yeah, I mean, and also quite often numerical simulations include all these different pressure components, so we do have a feel for those as well, and then compare with observations.
Can I respond to that?
Yeah. Okay, so Chris is going to talk about that.
Yeah, so there are two different kinds of instabilities. For dynamical instabilities, then you're completely correct. You have to include all the pressures. But for thermal instability, the other pressures are irrelevant. It just depends on what the density and the temperature of the gas are.
For the cooling, right? Cooling rate.
Yeah, but those are all thermal properties.
So I'm also mystified by the fact that the cold neutral medium, the warm neutral medium doesn't seem to change with galactocentric radius. And you said that maybe looking at other galaxies would give us some insight as to what's going on. Do you know, is there been any clue what's governing that ratio and why it doesn't change with radius?
Well, I mean, the reason I said that looking at other galaxies would be useful is because I think Adam showed this morning, looking at the different fractions in, say, compared the SMC, the LMC, Milky Way. This is John Dickey did this comparison there. And there, you would expect differences, and you do sort of see some differences, but I guess we don't have a very good feel for why they are coming out the way they do.
Any other questions? There's one in the back.
Yeah, so are you convinced that the bubbles actually do break out? That's to say, if you look really deep at H1, do you see caps? Has anybody done that?
Yes, so I am convinced. Not all do, some don't. But I didn't show an example that I do have of one where it goes very clearly, you go up 2 kiloparsecs and you see the cap starting, and it's broken apart into small scale features, and there's other ones where we don't see that at all. We go deep and we just don't see it. So I think in some cases they completely break out, in some cases they don't.
Okay, I see Enrique, but I would like to suggest that we stop with questions here and leave the rest of them for the coffee break. Let's thank Naomi again for a very nice review talk.